Hi, hello everybody. Let's begin. So my name is Aaron Filzer. I'm a faculty in the computer science department, and today I'll tell you about some aspects of my research. So the title is Metric Embeddings into Trees, and we'll begin by just discussing what a metric is. So a metric space, maybe some of you already saw them, it's a distance function basically. So you have some metric space, which is a set of points, and this D is just a function between, I give you 2 points, and this gives me a distance. And there are 3 axioms it should fulfill. The first one is the identity. This distance between any point to itself must be 0. And this is the only case where distance is 0. The second axiom is that the distance is symmetric. The distance from x to y equals the distance from y to x. And the final one is triangle inequality, which means given 3 points x, y, and z, the distance from x to y is smaller, or at least as large as the distance from x to z plus the distance from z to y. That is, going from x to y to z could only be larger than going directly. So let's see some examples. So the first and most important example for this lecture, at least, is shortest path distance in weighted graphs. So I have some graph, it might have some weights, and the shortest path distance is given 2 points u and c here. The distance between them is the weight, is the minimum weight of a path going from u to c. And this example is unweighted graph, and we have a path of length 3, so the distance is 3. And so let's see that it fulfills all the requirements. So the identity function, the distance from any point to itself is 0 using the empty path. It's symmetric because this graph is undirected, so we can just reverse every path. And finally, triangle inequality. So if I'm going from u to y and then to c, it could be only larger than going from u directly to c, right? Because this is the minimum over all the paths, and this is one possible path, right? So this is one example. Another example is eddy distance. So perhaps you already saw that. So this is distance between strings. Given 2 strings A and B, there are some edit operations you can perform, which is insert a new letter, delete a letter, and replace a letter with another letter. And the distance between 2 strings is the minimum number of this type of operations that you can do to, I guess this is better, the minimum number of operations you can do to go from A to B. So let's see an example. Here we have 2 words, definition and permission, and we have 7 operations that you can perform to get from definition to permission. So first we delete D, then we replace E by P, then we replace F by E, then we replace I by R, then we replace N by M, don't touch I, we insert here a new letter S, replace T by S, and we get permission. You also can think about this as a graph, where the vertices are all possible strings, and 2 strings are neighbors, and if you can go from the one to the other using a single operation. And this will be then a length 7 path. Another classic example is L1 distance, or Manhattan distance, which is distance above d-dimensional vectors. So here I give you all possible d-dimensional vectors, and given 2 vectors, the distance between them, which is the L1 distance, or Manhattan, is simply the sum over all the coordinates of the absolute value or the gap between the 2 coordinates. So here's example. Here, 5-dimensional vectors. And the L1 distance is simply summing up over all pairs distance in the coordinates. Yes, this should be a 1. So you sum them all up and you get the distance. So this as well, it's distance for any vector itself will be 0. It's symmetric because absolute value is symmetric. And it has triangle inequality, again, because of the same fact that absolute value fulfills triangle inequality. And final example I mentioned is Euclidean distance, which is basically, so we live in 3-dimensional Euclidean space. And this is very similar to L1. Well, here we go over square root of the sum of squares of the absolute values. Here again, same example. Okay. So this is the metric space, and a lot of problems in computer science or in general are defined over metric spaces. So here's some examples that you saw or will see in future courses: metric TSP, case center, standard tree. So for example, metric TSP, in this problem, we're given some metric space X, and the goal is to find a permutation over the metric points that will minimize the sum of various distances. So basically, think that you have a big metric space, and you want to go over all the vertices in the space. And you want to look for the shortest path possible, go over all of them. So how do you find this one? So here, for example, we have a map of the all the states in the United States of America, and this is one possible solution, going over all the states in some order. And the goal here is to determine the best possible order to go over the states to minimize the distance. Another way you can think about it is that you have a complete graph with all weights, and you're looking for a Hamiltonian cycle of minimum weight. So this is a classic problem, very central in our field. However, it's hard to solve. So specifically, this problem is NP-hard. So it's NP-hard. I guess some of you saw, maybe not everybody. NP-hard is a large class of equivalent problems. Equivalent means that if you solve one, you solve all. It contains lots of problems. Most of the major problems in the field are NP-hard, and we don't know how to solve them efficiently. I mean, other than just going all the possible options, like here in PSP, for example, there's n factorial options. We can go over all of them and take the minimum. But this will take you exponential time. So if you want to do it in polynomial time, we don't know how to do it. We believe it's impossible. And yeah, I said there's a long list. This is like the classic list of problems from 50 years ago, more. But by now it's much larger, and we know about a lot of problems that are hard. So how can we cope with problems we don't know how to solve exactly? So there are many different ways, and the major one is approximation. And right, so instead of solving exactly TSP, for example, I will find some Hamiltonian path, which will be not much larger than the optimal path. And how can I solve? How can I approximate such things? So there are many different techniques, and one of these techniques called metric embeddings. So metric embeddings is also useful for other things than approximation algorithms, but today we'll talk about approximation algorithms mainly. And the idea that given some general graph or geometric space, problems are very hard to solve. However, if the metric space will have more structure, for example, if it will be low-dimensional Euclidean space with a planar graph or tree, some simple structure, it could be utilized to perform better and more efficient algorithms. And the idea is that I take my complicated metric space and I transform it into some simpler structure while preserving, hopefully, the properties of the metric space, and then I can run my efficient algorithm in the simple space and somehow deduce the solution in the original problem. In metric embeddings, we basically want to preserve many different properties. Properties could be distances, which is the main topic of today, but also other, like maybe some other statistics, like cuts and flows, if it's a graph, commute time, effective resistance, some other clustering statistics. Yeah, if you don't know what it means, just ignore it. So we'll focus on distances. And what I mean by preserving distances is that for every 2 points, the distance in the embedded space will be at least as large as the original distance, at most p times larger. If you can do that, then this thing called distortion T. This metric embedding with distortion T. That is, you preserve the geometry of the original metric space up to a T factor. And hopefully you can make some algorithms here and take it back and only paying this distortion T for this transformation. So yeah, so the goal basically is to minimize the distortion and the simplicity, if you like, of the target space. Yeah. So let's see one example. So this is the definition, and this is a simple graph. Basically, this is just a star with 3 leaves or a tree, and the distances here. So the distance from the vertex A to all the others is just 1, and between any 2 other vertices, the distance is 2. And this is the matrix of all the metric distances. So this is basically the distance function. And now suppose that I want to embed it into the Euclidean plane. So how can I do it? So the Euclidean plane is just like on a piece of paper. You want to put it on a piece of paper and you want to preserve all distances. However, know that in a piece of paper, the distance between 2 points is not the shortest path, but the straight line. Right? So the most natural thing to try is just to put the same thing. Right? So you put A at the center, and this will be equal to a triangle, such that every vertex is distance 1 from the center. Right? So all the angles are like exactly 120 degrees. And this is the most natural thing to try. However, note now that the distance between, say, B and C is square root of 3 instead of 2. So this does not fulfill the requirement. It's not a valid metric embedding because some distances become smaller. So how should I fix it? Yeah, just scale it up, right? So I slightly scale it up, and now the distances here will be exactly 2, which is the minimum requirement, but now the distance from the center to all the others is slightly increased. Instead of being 1 as before, it's now 2 over square root of 3. So what will be the distortion of this embedding? Exactly. Yeah, this is the maximum distance, and this is the distortion. So actually, I'm not sure if this is the best possible, but it's clearly impossible to do isomorphic, that you cannot preserve it perfectly. A piece of paper is not rich enough to represent this simple tree. And actually, even if you add more dimensions, you can slightly improve the distortion, but you'll never get exact. I mean, there's some hard lower bound, even infinite number of dimensions will not help you. Okay, so yeah, this is distortion. So let's go over some of the classical results in this field. So the first one is a result by Bourgain, who showed that every metric space with n points can be embedded into Euclidean space with distortion log n. So this basically tells you that no matter where you start with, after performing this transformation, you can assume that your points are in Euclidean space. The dimension is actually log n here, but you only paying distortion log n, and after paying this log n, that's it. Your points are in Euclidean space. It could be utilized for many algorithmic applications. And this is actually also known to be tight, in the sense that there are some metric space that no better embedding exists than with distortion log n. It has applications for some approximation algorithms. So one of them is sparsest cut, which is a more complicated and useful version of minimum cut that you saw in algorithms. Kind of keeps the sides balanced in the same time. It's not only looking for the minimum cut, also used for some parallel computation, computational biology, etc. So here another result by Rao, who says that in a sense, so this is also embedding into Euclidean space. So the previous one was from general metric space, which could be quite crazy. And here Rao said that suppose that my metric space is simpler. For example, it's the shortest path distance of a planar graph. Then one can embed into Euclidean space with distortion square root log n. So this is a quadratic improvement, assuming you started from a simpler space. And this is also tight, meaning there are some planar graph such that cannot be embedded better than with distortion square root log n. Clear? So this one is super useful metric embedding by Johnson and Lindenstrauss. So this is from Euclidean space to Euclidean space, but from a high dimensional Euclidean space to a lower. And what they show is that given endpoints in Euclidean space, so the dimension could be basically unbounded, but I mean, basically on stuff you saw in linear algebra, you always can reduce to dimension n-1, and by Gram-Schmidt. And they show that you actually can reduce the dimension log n over epsilon square while paying only distortion 1 plus epsilon. This means you almost perfectly preserve all the distances up to 1 plus epsilon factor, while the distortion now is only logarithmic. sorry, not distortion, the dimension. This means that actually you always can assume that the number of dimensions is most log n. Think nowadays when you collect some data, usually you have like numerous coordinates representing lots of different stuff, maybe even more than number of points. And this can give you that you always can assume that the dimension is log, and you're paying for it only slightly. And this is also tight. There are sets of points such that you indeed need this number of coordinates to preserve all distances up to 1 plus epsilon factor. And this is used to speed up computation. Now the dimension is small for clustering, nearest neighbor search, and various of machine learning applications. We shall now go over. No, if you start with 10 dimension, the number of points is large, it might be possible that you cannot reduce it in 1 dimension. Right, yeah. But it says that if you think that the number of points is large, then you can always use to log n dimensions. If you start with lower than log n, that's that. Doesn't give you anything. Other questions? Okay. And here's another example that maybe you already saw, graph spanners. So think that graphs basically could be with quadratic number of edges. And I would like to find a sparse subgraph that will preserve all distances. This is a T-spanner, is a subgraph H, such that for every 2 points, two vertices U and V, the distance in the subgraph could not decrease because it's a subgraph, but it increases by at most a T factor. And the goal here is to preserve distances while minimizing the number of edges in your graph. And as was shown by Altofer et al., for every integer k, one can construct a spanner of a stretch or distortion 2k minus 1 and n to the 1 plus 1 over k edges. And yeah, so basically, if you want, say, distortion log n, like in Bourgain, you can get linear size. So any graph contains a linear size subgraph, preserving all distances up to log n factor. And there's a smooth trade-off. As you increase number of edges, the distortion will decrease as well until for k equals, say, 1, you get exact 1 spanner, but the number of edges is quadratic. You didn't save anything here. And this is as well tight up to some conjecture by Erdos that actually is open for lots of time, and we don't really know how to solve it. But I mean, without this conjecture, we know to prove that, let's say, 3k here cannot be improved. So this was lots of different examples of what metric embeddings are. Yeah, this is also lots of applications. Actually, the p-test for TSP, the Euclidean space goes through spanners. Anyhow, so the topic of today is stochastic, is embedding into trees. So as I said, so if you didn't follow the previous examples, doesn't matter. We start now. Just the definition of embedding is important, so I hope you got that one. And now we start with the main topic, actually, which is embedding into trees. So trees is very desirable target space, right? Trees are very simple, and basically almost any problem you can just solve by dynamic programming on a tree. So lots of NP-hard problems become easy once you go to a tree. However, trees are not very representative. So consider this super simple graph, just a cycle, and suppose I want to embed it into a tree. So what I can do, I can delete some edge, right? But what will be the distortion? So if I delete this edge, this, so what distortion is the, I'll go back to this definition here. Here, this definition. The distortion is the T such that this inequality will hold for every pair of points. This is the minimum T such that for every 2 points, distance will increase by at most a T factor. So now, if here I delete, say, this edge from 0 to 1, what will be the distance from 0 to 1 now? So it's n minus 1. Originally, it was 1. And this is the worst possible distortion for every pair. So the distortion is n minus 1. And I mean, so this is, the tree is not necessarily a subgraph. You can maybe embed to a different tree, but you can prove that you can never get much better than that. N is basically the best possible distortion. So I mean, this looks like the end of the story because, I mean, yes, trees are great to embed into because they're very simple from the one hand, but from the other hand, they're not very representative. So you cannot represent interesting, even this simple metric using a tree. However, let's suppose that we delete a random edge. What will be the expected distance from, say, vi to vi plus 1, or v0 to v1? So fix some pair of neighbors. What now is the expected distance if I delete a random edge? So if I delete the edge between vi to vi plus 1, this is terrible, because now the distance is n minus 1. But if I delete any other edge, then great, the distance is still 1. So what's the probability that I delete this exact edge? Exactly 1 over n. Well, any other edge is n minus 1 over n. And overall, this is at most less than 2. So now the expected distance from vi to vi plus 1 is at most 2. So it's good. And this is actually true even for any pair, not only pairs of neighbors. So consider that I take some vi and vj, then I can break the path from vi to vj to like going from vi to vi plus 1, then to I plus 2, and so on. And then by linearity of expectation, I can take the sum out of the expectation. And I get that the expected distance from vi to vj is the sum of expected distances between any pair of consecutive neighbors. And this one, you already know it's at most 2. So overall, I got twice the distance from I to j. So overall, if in a cycle I delete a random edge, I get that all the distances are preserved in expectation, up to a factor of 2. And as we'll see, this turned to be quite useful because expected distances could be good enough for many applications. Well, we're in trees and we like working with trees. So this could be generalized to any metric space, as was shown by Fakashiroko, Rao, and Talwar, improving previous works by Bartal. Any endpoint metric space could be embedded into distribution over dominating trees with expected distortion log n. So this is quite a mouthful. Let's break down this theorem. So I have some metric space, let's say a weighted graph with a short path distance. I can embed it into distribution over trees. So there's all of them, just trees over these points v. In some trees, the distance from v and u, say, could be great. In some of them, it will be terrible. In some of them, will be okay, right? And all of them is just distribution over trees. I have some distribution when I sample a tree. So for example, in the cycle, my distribution was all the paths when I deleted a single edge. So the support was n, and I have n trees in the distribution. Now, all these trees are dominating in the sense that in no tree, any distance could decrease. So in any tree, and for every pair of points, the distance in the tree will be at least as large as the original distance. And the final requirement is that the expected distortion is log n. So if you fix a pair of points, u and v, and you come the expectation over the distance between them when you sample a tree from this distribution, then the expected distance will be at most log n times larger than the original distance. So here, for example, the distance is like exactly right. Here is slightly larger. Here is much larger. And if you take the random tree, the expected distance will be at most log n times the original distance. So in the cycle, we saw the expected distance was at most twice the original one, and here is at most log n times. Yeah. Right. Right. Here, all the edges are equal. Here, I mean, I just draw a graph, but I mean, think of a metric space. It's like a weighted graph is general. Not really. What do you mean? Why not? I mean, a weighted graph is a generalization of unweighted graphs. What do you mean? I don't really. I mean, the tree is just some general graph. It also can have weights. Yeah. No, it's not. No, I'm not proving this theorem. I'm not saying. I mean, this theorem is quite complicated. It took us. I mean, it's not very complicated to prove, but it took us as humanity like a long time to come with it. It's not something that I can like, have my ones and explain. It's not like. I mean, the intuition from the cycles just comes to show that it could be done in some simple graph. How you do it here, I didn't explain. I mean, it's not something I can explain standing on one leg. If you want, I can explain at the end of the lecture how you can get log square here. This will take about 15 minutes, but this one is also not very complicated, but it's quite tricky. Okay. Other questions? Okay, and this is also tight. Actually, this was known. We have the lower bound way before the upper bound in this case. Initially, they proved upper bound of something on the scale of 2 to the square root log n. And the next result was log square, then log n of log n, and like only after, I guess, almost a decade of effort, we got the exact log n. And actually, it's tight, even like the alone Pelag West lower bound is just a grid. Meaning, if you take this graph, the grid, meaning you have like just n square points or like square root n or square root n, and everyone have neighbors to like think of it's like in coordinates to all the neighbors. If you change one coordinate one, this is the grid graph, like planar graph. It's very simple, but even this graph could not be embedded better than when expected distortion log n the trees. And this is a very useful hammer because it transforms every metric space into a tree. As I said, trees are very simple and friendly for the algorithm designer. And it has applications for online approximation algorithms. This is actually throughout the field. It was very useful. So the plan for the rest of the lecture is to show you 2 applications of this tool. One to distance oracle, and the other one to the group time tree problem. So what's a distance oracle? So suppose you have some metric space or a weighted graph, and you want to prepare to be able to answer some distance queries efficiently. So you prepared your data structure, and then I'll come and ask you, what's the distance between x and y? And you should efficiently be able to answer this query. So yeah. So given endpoint metric space or weighted graph, you can simply store all pairwise distances. And then you can answer very efficiently, right? It will take you n square storage to store everything. But once you store everything, given a query, you can simply answer from your table. And this is query time 1. But usually, quadratic space could be too large for some goals, especially today with these huge data sets. So we want to do something better. But this is best possible for exact. So in order to improve the space, the storage, one need to allow some to return approximate distances. Instead of returning the exact distance, if I return you something which is approximate distance up to the factor t, perhaps I can do better than quadratic space. Yeah, and the properties we care about here is 3 properties. So size, the space that you store, the query time, so constant is great, maybe slightly more, and distortion, or like we want to approximate distance to return as best as possible. So how can we create a good tree using these stochastic tree embeddings? There's no dimensions here. Just think of like big weighted graph. It's not living in Euclidean space, and I want somehow to answer quickly queries. So I mean, this is like a very basic application. It's not, yeah. So Suppose that I fix a pair of points and I sample a tree from this distribution. What I will get is the expected distance will be at most log n times larger. And the idea will be simply to sample many trees. So in this case, log n different trees. So I'm sampling log n different trees. And given a query x and y, I will go over all the trees. In every tree, I'll compute the distance from x and y. I will also prepare for that. It will be easier because it's a tree. And I will return the minimum observed distance. So there is a data structure that given a tree computes the distance in the tree in constant time with constant approximation. And actually, in the trees with the structure that we have from this theorem, which are not general, this is a more special type of trees, we can even get exact distances in constant time. So from the one hand, clearly, as all the trees are dominating, that is, no distance becomes smaller in any tree, the minimum distance will be at least as large as the original distance. You have some question? It's not again, it's not something simple. I mean, it's not super hard, but it will take me, I guess, about half an hour to explain. I mean, the result, yeah, some simple data structure tricks. Yeah, it's not the topic of the lecture, but it's like the one from this one is like LSA type of answers. Given that like you can't structure a tree such that the distance will be dominated by the least common ancestor, the LSA, and finding the LSA could be done very efficiently. This is basically the idea. Not LCA, sorry, least common ancestor. Okay, so clearly all the distances become only larger because this is the case in every tree. So now I want to prove that the distances will not become much larger. So how do I prove that? So this is just basic probability. So recall Markov inequality that says that the probability that some random variable is larger than A is bounded by the expected size of X of the random variable divided by A. This is only for positive random variables, but it's fine because this is always positive. And now this means that the probability that the distance from xy will be twice larger than the expected distance is just by Markov inequality the expected distance divided by this number, which is twice the expected distance. This is just a half. Meaning that by Markov inequality, the probability that you get twice the expected distance is at most half. Okay, but what I do here is I sample log entries and return the minimum. So what should happen so that the distance oracle will return something which is twice larger than the original distance? So this should happen in all the trees that I sampled, right? So for every tree that I sampled, the distance should be twice larger than the original distance, than the expected, distance. But I mean, all these trees are sampled independently. So the probability that this happen in every tree is independent. So basically for this to happen, this should happen in all the trees. So I can like take the, because they're independent, this event should happen S times. But by Markov, we said that the probability that in every specific tree, the return distance is twice larger than the expectation happens with probability at most half. So the probability of this event is at most half in the power of the number of attempts, which is S, and I chose S exactly for log n. So this is at most 1 over, say, n to the 4. So this is highly unlikely. And by union bound, because I have only n square pairs, the probability that this event happens in one of them is at most 1 over n square. So this is, again, very unlikely. So assuming this doesn't happen anywhere, I will get a distance, so I will get like a collection of trees so that every pair of points is preserved up to a log n factor in at least one of them. And accordingly, for every pair x and y, the distance oracle would be at most twice the expected distance in one tree, which is just a log n. Right? And so the space, let's see what we got here. So this is this circle. What's storing trees? So storing trees is just linear space. I need to store log n trees. So my space will be n log n. And we, by the way, count space in machine words. And then for the query time, we just need to go over all the trees, and in every tree we check what's the distance. So I will again prepare for that, as we discussed before. There is some mysterious data structure that can return for every tree order one approximate distances in constant time. And actually for the trees returned by the FRT, we can do even exact distances in constant time. So overall, this is just equivalent to the number of trees, which is log n. So we got a log n approximation with log n query time and almost linear space. So this is nice because I think that if you want to, in general, given some graph, for example, to give you the distance between 2 points, will take you usually linear time, like using Dijkstra or whatever. While here, with some preparation, you can get it with log n time. So actually, this is not the state of the art. The state of the art is by Chechik, who showed that one can get approximation log n, as we got, but with linear, really linear space. We got here n log n, and with actually constant time. Yeah, but I will not be able to explain this one as well. But one of the components, this result is tree embeddings. I mean, it starts by getting some approximation very quickly using trees, and then it's continued to improve. And actually, you can even get a smooth trade-off for all approximation factors. So you can get approximation 2k minus 1 using space n to the 1 plus 1 over k and constant query time. So note, by the way, this is the same trade-off as with this spanners that we mentioned. This is again tied up to this Ardous-Gers conjecture. Okay. Any questions about distance oracle? Yeah. No, if you have, if it's Euclidean space, you don't need to do any distance oracle just to compute. You just compute the Euclidean distance. So this is what the so think that Euclidean distances, you have the vector. So computing distance is a simple task. I mean, I mean, just take the coordinates and compare them. The hard task of computing distances is the graph, right? Because given S and T, how do you compute distance? So you run Dijkstra. But this consumes a lot of time, so you don't want to do it. So you want to prepare. Right, yeah. But if you have high dimensional Euclidean space, for example, then yeah, we'll use Johnson-Wiener-Strauss, we'll reduce the dimension to log n, and then to compute distance will take you log n time. And yeah, I mean, if you're willing to suffer mistakes with low probability, you can do it faster. Because then you can do less than log n dimensions. But if you want to be successful all the time, then yeah, this is the best thing you know of log n time. More questions? Okay, so let's go now over to the next application. So this application to approximation algorithms, how many of you saw approximation algorithms before? Please raise your hands. Okay, so not a lot. So I guess it will be a crash introduction to what approximation algorithms are at the same time. So we'll start with the problem you're all familiar with, minimum spanning tree. The minimum spanning tree is just, I give you a graph, and you want to find the minimum weight tree that spans all the vertices. Like in this case, it's this one, and you saw two algorithms, Kruskal and Prim. There are many others, and these are super efficient, like linear time, or n log n if this number of edges is too small, and that's that. A more complicated version, yeah, it's all in polytime. A more complicated version called Steiner tree. So in this case, in addition to the graph, I also get a subset of terminals, denoted here by K. And the goal is to find a minimum weight tree, or forest in this case, that spans all the terminals. For non-terminals, you can either span them or not. This example of a Steiner tree. It spans this vertex, this Steiner points, but this one are not. And it spans all the terminals. And the Steiner tree problem, the goal is to find a tree of minimum weight that spans all the terminals. So this problem is already NP hard. That is, we don't know if any efficient algorithm to solve it. We believe there's no such algorithm. But in there, there's this very simple two approximation algorithm. And actually, the best known factor is 1.3 something. I don't remember exactly, but there's some lower bound as well. I mean, you cannot get 1 plus epsilon or something like that. And this is classic Steiner tree problem. And the application will show you it's So let's see exactly what I mean by two approximation. So approximation algorithm before. So there is a very simple polynomial time algorithm. So I had given an instance of the Steiner tree problem after some polynomial time, returns you a Steiner tree, and with the promise that the weight of the Steiner tree is at most twice the weight of the optimal Steiner tree for this problem. So the weight of the alg is at most twice the weight of the opt. And it's do it in polynomial time. Okay, so this is the problem we actually discuss now. It's called group Steiner tree. So group Steiner tree is like Steiner tree on steroids. I guess think of Steiner tree, for example, you have some infrastructure, like some sites, and you want to build a road. And you're thinking, what is the minimum amount of road that I can build to connect all the sites? So you have many different options around where to put this road where, and this is the Steiner tree problem. Now the group Steiner tree is this version when suppose that you like put a new village and you want to connect yourself to maybe a well and maybe some mines and so on. But there's many of them. You can choose which one to connect to. So in this problem, in addition, instead of terminals, you get k different groups, G1, G2, Gk, which is just subset of vertices. They could also intersect. So in this example here, you have three groups. The blue one is this, and this. The green one is this four vertices, and the purple one. And the goal is to find a minimum weight tree or forest that spans at least one vertex from each group. Yeah. So it's not edges, it's vertices. Yeah, there could be one vertex that belongs to several groups. It's allowed. Other questions? So let's look for some solution to this problem. So here, this is a tree. Suppose this graph is unweighted. Then the weight of the solution is 5. And it spans one vertex from each group, at least. In this case, exactly. Is this the best possible? No. Here's an example with weight 3. Still spanning one vertex from each group. Is this the best possible? No? Right. So here's a solution with 2 edges. And I think this is the best possible. No, this is. But however, I mean, finding this is much harder than just a Steiner tree. And note that, for example, if every group has size exactly 1, this is just the classic Steiner tree problem, where we have a very good approximation, some 1.3 or something. However, the group Steiner tree is much harder. I think it's a combination of like set cover and Steiner tree together. So first you need to choose which vertex to cover from each group, or like a hitting set, and then you need to find how to connect them all. So this problem is much harder. It's actually already hard even on trees. You can do reduction to set cover or hitting set. You saw these problems. If yes, good. If not, doesn't matter. We'll see it in the future. So these also like basic NP hard problems. So even on trees, this problem is already hard. However, for trees, we have some smart approximation algorithms by Gar, Konjev, and Ravi. So they showed that given the case of a group standard tree problem on a tree, so think even on a tree, it's not simple because we'll draw something. So even on on a tree, for example, thing that this is like the reduction. Like basically, so this all weights are 1, and these all weights are 0. And once you pick a 1, you can like connect everything in a subtree. So basically, this is just a set cover problem. So in this problem is known to be very hard, just this case, with log and lower bound on approximation factors. So we know that you cannot approximate group symmetry on trees better than log n. And here the approximation factor is log n log k. K here is the number of groups in the problem. And what we want to do is to generalize. So we'll not discuss how they do it. It's again some complicated algorithm, but what we'll see, it will be simple, is how to reduce from this problem on a tree to a problem on general graphs, which is, I mean, in trees, at least seems that somehow approachable. On general graphs directly, it's completely unclear how to solve. And the idea is to take a general graph, reduce it to a tree using stochastic tree embeddings, and then to use the algorithm of Garg et al. As a black box to obtain approximation algorithm for general graphs. Yeah, so, so let me again say exactly what I mean by Garg et al. Find the log and log k approximation algorithm for group standard tree. So it means that given a tree T, could be weighted as well, doesn't matter, and k groups, there is an efficient algorithm. Efficient means runs in polynomial time. It finds a subtree T alg, spanning a subset of the vertices, such that for every group GI, it spans at least one vertex, and the weight of the return algorithm T alg get most log n log k times larger than the optimal algorithm possible, than the optimal tree or optimal solution for this instance. Okay, it's clear? And we will use stochastic tree embeddings to generalize Garg et al. Result. So this is the picture. So we're given k subsets, G1, G2, up to Gk. And the goal is to find a minimum weight 3T, spanning at least one vertex from any group Gi. So suppose this is the instance. So we have 4 groups, and we have some graph, and this is the groups. And what I do is simply sample one tree with expected distortion log n. Right, this is the FRT result. So this is a tree I sample. Now the idea is that, this is actually usually the idea. So I have my graph. I embed it into a tree. Now I want to embed the problem as well somehow, solve the problem on the tree, and take back the solution to my graph. And hopefully what I'll pay is only this expected distortion log n. So how will I transfer the problem into a tree? Just simply take the same groups. So it's like one-to-one embedding, and every vertex, which was in like group G1, will be now in G1, called G1 prime because it's different graph, but it's the same group basically. And all the greens will be the same ones, and the yellows and reds and so on. So every group will be simply a perfect image of the group in the graph. And now the algorithms will simply be to find a solution using Garg et al. Algorithm entry and take it back. But in the proof, I'll kind of start with an optimal solution, which I don't actually know, and use it to argue that the solution that I will find is actually a good approximation. So consider an optimal solution to the problem. We call it S star. This is this pink graph here. So I'm not sure if it's optimal, but it's good enough. Suppose it's optimal. And now, using this graph, this optimal solution that I don't know, S star, I construct a good solution, S star T, in the tree. And how do I do that? So for every edge UV in S star, I'm adding the shortest, the unique path in the tree from U to V. So there's an edge here, 15, 16. So I'm adding the path from 15 to 16 to S star T. And then there's an edge 12, 16. So I'm adding this path. And then 16, 17, so I'm adding this path. And then 17, 19, so I'm adding this path. And eventually I get some tree, some sub tree, the big tree, which I call S star T. What can I say about the weight of this image, S star T? So I can say that the expected weight of S star T is at most the sum of expected weights of the path I added. So note that here, many of the paths overlapped. And for each such overlap, I will pay only once. However, I ignore that. I just use inequality. I say the weight of S star T is at most the sum of the weights of the path I added. So each such path is the distance in the tree between U and V. I know that in expectation, each such distance is increased by at most a log n factor expectation. Right? So I have here log n times the sum. This should ignore this line. Should be immediately this line. So each such thing is at most log n times the weight of the edge in the original graph. So I take the log n out. Here I have this sum of weights, and this is exactly the weight of the optimal symmetry S star, because I just go over all the weights of all the edges there. So I got an expectation. My tree T contains a solution S star T of weight at most log n times the optimal solution, an expectation. Okay, so this is just a fact to prove about this embedding. So even though originally the embedding preserves only pair resistances, now I showed you that it actually preserves, in addition, the optimal solution to the group standard tree problem in expectation. I don't. No, I can't promise that. I didn't argue that. I just say that this tree contains a good solution in expectation. I don't know how to find it. But what I know how to find is approximation in the tree, not in the graph, in the tree, right? So now I can use, so this is what I know, and now I can use this Gard et al. Algorithm, which finds a log and log approximation in trees. So here I have some group symmetry problem in a tree, and I argued before that in expectation it contains a good solution. And now I don't know anything about that, but I just run a black box known algorithm, and I found this tree, which I call S tilde T, which is at most log n log k times larger than the optimal solution in the tree. Now, S star T is not the optimal solution in the tree, but this is a solution in the tree. And therefore, the weight of my solution S tilde T will be at most S star T, at most log n log k times larger than the optimal, which is at most log n log k times the specific solution S star T. Right? Now we can do the last step. We want to transfer this tree that I found, that I can't find efficiently, and to a solution to the original problem. But the original problem was in the graph, not in a tree. So how do I do that? So for every pair of points, V prime, U prime, sorry, for every edge in the tree, V prime, U prime, I'll take the shortest path in the graph between these 2 points. So for every edge here, say one tree, I take the shortest path in the graph and so on. So in this case, it's the same one, but in general, it could be some complicated thing. It's actually not necessarily even a tree. But if it's not a tree, it's not a problem. Just remove some edges until it will be a tree, right? I mean, you can, in the standard tree, group standard tree problem, if you return something which is not a tree, as long as it's connected, it's fine. Just remove some edges until it will be a tree. So this is S tilde. which is just the union over all the shortest path between any two. For any edge in the tree, I take the shortest path between them in the graph. And I argue this will be a valid solution, right? So because it will be connected, if you start with a connected thing and you add a path between them, the result will still be connected. It will span a single vertex from every group at least, because the original thing here spanned at least one vertex from every group. And okay, so this is not a valid solution. There's no red here, but ignore that. Let's say 8 is red. Right, so I just return a valid solution. Yes. So it's a good question. In this example, it is a spanning tree. In general, actually, it's not a spanning tree. You can do it with spanning trees. You don't know to do log n. You know how to get log n, log n. But actually, it's only spanning tree in the picture. In the argument itself, there's no requirements of this being a spanning tree. Other questions? Yeah. Okay, so now I just need to argue about what's the expected weight of this return solution S tilde. So let's see. So the expected weight of this solution S tilde is smaller than the expected size of this tree S tilde T. And why is that? Because I take every edge here, and this tree is dominating. So the weight of the shortest path from every pair here is at most the size of the edge. It could be smaller, but it can't be larger. So I have that the weight of S tilde, the tree in the graph, is at most as the weight of the tree of this like subtree in the tree. Now we argue that the tree S tilde T is at most log K log n times larger than S star T, right? This is because using this Garget algorithm, and now S star T is an approximation algorithm of this was using Garget al. So it's log n log k times the expected size of S star T, and S star T, as you recall, is log n times larger than the optimal in expectation, right? Because we saw that stochastic tree embeddings also preserve group standard trees up to log n factor, and therefore I get here that the expectation S tilde is at most log n times log k times the optimum solution. So overall, I got log square n log k approximation algorithm in expectation. Right? Questions? Okay, so how can I transform it into a high probability guarantee? So usually in approximation algorithms, I want to give a valid solution, not only an expectation. So how can I get? Yeah, exactly. So it's pretty the same as we did before. I just will run it log n times, and I will return the minimum observed solution. So all the solutions that we'll get, they will all be valid. And with high probability, the minimum one will indeed be at most log square n log k times larger than the optimum. That's that. Okay, so let me wrap up. So this lecture was about metric embeddings. So an embedding is a function between some two metric spaces that preserve all pairwise distances up to a t factor. And we saw that it's usually impossible to get distortion 1. So even here in the star graph, and when we want to embed it into a Euclidean space, we need to pay some distortion. And the main topic was stochastic tree embeddings, which is embedding of any metric space or weighted graph into distribution over trees that preserve all pairwise distances up to a log n factor, but only an expectation. Right? So it's impossible to do it exactly like in this definition because trees are not representative enough, but it's impossible to do it in expectation. And then we saw two applications, lots of them. One of them was a very simple construction of a distance oracle, just sample log n trees, check the distances any one of them and return the minimum observed distance. And we saw that it gives you actually not much worse than the best possible log n approximation with log n query time and log n space. And finally, we saw an approximation algorithm for the very complicated problem of group sign tree. This, by the way, is the best known. You saw, I mean, up to this Gargetaro, I mean, the gist of this algorithm actually is the approximation algorithm of the tree itself. But the generalization to general graphs is quite simple, as you saw. And yeah. So let me say that I'm looking for master students. So if you're looking for a master and like this lecture, please come and talk to me. If you enjoy theory, enjoy designing algorithms, there are many open problems in the field. I mean, so didn't solve some of them, but there are really lots of them. The field is young. Yeah, so there are many challenging problems in the general scholarship waiting just for excellent students or for you. And you can find a lot about my research from my homepage. So here. I think I don't have internet. Yeah, I don't have internet. Anyhow, if you just go to my homepage, there are lots of videos. I gave the same lecture previous year, but previous year we have a different, oh, here it is. This is my homepage. You can just Google Arnold filter, and here are videos. And you see this video here is of the same lecture I gave last year. However, last year, all the students were assumed to take advanced algorithms course before this lecture, or at least be in the middle of the course. So I actually gave much more details, and I mean, the lecture was deeper. So if you enjoy this lecture after the online algorithms, advanced algorithms course, you're welcome to watch this one. And you can also see that the field is indeed quite rich, lots of publications. Okay, let's go here. And now we came to the last part, which is the quiz. So there are 3 questions. This one is a warm-up question. Let me just tell you about this question. So here, there is a specific metric embedding from the cycle graph into the line. So this is just a cycle graph. Distances are short paths. Distance from V1 to V2 is 1, from V1 to V3 is 2, and so on. And then embedded into the line. So 1 goes to 1, 2 goes to 2, and so on. And the question is simply, what's the distortion? This is the first question. Now the second question, the 2 second questions is a bit more interesting. So suppose that there's a graph family called Graphica prime, which is some imaginary graph family, such that every graph in this family, Graphica prime, embeds into the distribution over dominating trees with expected distortion T. So, I mean, so previously we had this FRT result. We said that every metric embedded into the distribution of the trees with expected distortion log n. Now, there's some mysterious graph family called Graphica prime, which has the exact same result, with the only difference that the distortion is T, which is some constant, instead of log n. And now the question is, using the same techniques, the ideas that we use in class, what distance oracle can you achieve for graphs in Graphica prime, and what approximation factor can you achieve for the group sign tree problem for graphs in Graphica prime? And you can find please answer the quiz using this link, and you can find the slides using this link. And if this doesn't work for you for some reason, just Google Arnold filter in a new website. In the first page, in the lower part, you'll find links for quiz and links.